Hello everyone, my name is Sunder Rajan. I am currently pursuing BE Mechanical Engineering in Coimbatore Institute of Technology. Today I am going to give a presentation on the topic ion implantation and diffusion coating. First, let's have a look at ion implantation. Ion implantation is a low temperature process by which ions of one element are accelerated into a solid target, thereby changing the physical, chemical or electrical properties of the target. Ion implantation is used in semiconductor device fabrication and in metal finishing as well as in material science research. It is a surface treatment process in which ions of nitrogen or carbon are accelerated and made to penetrate the surface of a component to impair wear resistant. In other words, ion implantation may be defined as the process by which energetic impurity atoms can be introduced into a single crystal substrate in order to change its electronic properties. So this process is clearly a surface treatment process and not a surface coating process. Ion implantation is a batch process. That means it cannot be done together as a whole, but it should be done batch by batch, and it has a treatment time of about 2 to 10 hours. The process is much more reproducible and controllable than most other conventional surface treatments. After ion implantation, the component's surface requires no further treatment prior to use. That means it doesn't need any other surface treatment process as soon as this process has been completed, such as the heat treatment process or the other processes which should be done before being put into use. This is a huge advantage. The implantation depths range from about 0.1 to 0.3 micrometer. This process is analogous or similar to diffusion process such as carburizing, nitriding, but requires much more substrate temperature of about 200 degrees Celsius, which means that this process can easily be carried out at very low temperature when compared to other processes, and this is also an advantage of this process. The ion implantation can be carried out virtually on all ferrous and non-ferrous materials, but it is presently used only mainly for steels and cemented carbides. The process can be steadily and readily applied to components that already have surface coating, such as chrome plating. As I told you, the depths range from 0.1 to 0.3 micrometer, but it is purely independent and we may use any other depths as per our requirements. So it is not a compulsion that the implantation depths must range from 0.1 to 0.3 micrometer, but we have the independent choice to choose our own depths, and we can purely choose it as per our usage. Working principle. The ion implantation equipment typically consists of an ion source where the ions of the desired elements are produced, and in an accelerator where the ions are electrostatically accelerated to high energy, and in a target chamber where the ions impinge on a target, which is the material to be implanted. This is the image of the ion implantation system, and I'll explain each and every component of the system and how it is used. This is the real life ion implantation system. As you can see, the process takes place in this chamber, and you can have a real-time update on this monitor where you can change the input or get the necessary information. Okay, now I'll explain the ion implantation system. So initially, the gas containing the desired impurity is ionized within the ion source. This is the ion source. The ions are generated and repelled from their source in a diverging beam focused by the first electrical lens before it passes through the mass separator. So the first electrical lens, which is present here, diverges the beam and it sends to the mass separator. The mass separator consists of an electromagnet which is used in separating the magnetic impurities from the ions. The second electrical lens focuses this resolved beam and then it passes through the accelerator. As you can see, this is the second electrical lens, and the ions coming out of this mass separator are passed through this second electrical lens, which then diverts the beam into the accelerator. The accelerator brings the ions to the required energy before they strike on the target and become implanted in the exposed area of the silicon wafers. That is, the accelerator which is present here will accelerate the ions to the higher energy which passes through the second electrical lens before being sent into the target chamber. In the target chamber, the dopant atoms are vaporized, accelerated and directed at the silicon substrate, which is also known as wafer, and they enter the crystal lattice, collide with the silicon atom, gradually loses energy and finally comes to rest at some depth within the lattice. So as I told, these are the parts which are present in the ion implantation system, and I explained the usage earlier, the workings earlier. So let's come to the advantages of the ion implantation process. The advantages of the ion implantation process is that it is used to obtain highly pure form of impurity atoms, and a wide range of dopant doses can be used. So depending upon our requirements, we can use any dose, because there is a wide range of dopant doses present, and we can choose any among them. And another important advantage of this ion implantation process is that this process can, as I told earlier, can be performed at a very low temperature, very low in the sense it can also be carried out at room temperature, and this process provides an independent control of dose and penetration depth. As I told earlier, both the doses and the penetration depths is purely independent, and we can choose as per our usage. The disadvantages of this process is the equipments which are used in this process are highly sophisticated and expensive, so it is not easily accessible, and it results in damage to the conductor. So often we have to replace the conductor, and as I told earlier, this is going to be an expensive process again. And since this process is carried out at very low temperature, when we carry out this process in very high temperature, and the process of annealing is needed to be done. Let's check out the application of the ion implantation process. The ion implantation process is applied almost in every field, and it is a very important process. Some of the applications are they are used in plastics, polymers and elastomers, and in pharmaceutical industries they are used in the treatment of seals, washes, etc., and in medical industries they are used in syringes, caps, membranes, silicone implants, etc., and in car parts it's used in V-seals, lip seals, O-ring seals, connectors, etc., and in metal parts they are used in the treatment of titanium, aluminum and precious metals, etc., and it is used in precision compounds and micromechanisms, high-tech parts for the aeronautical and defense industries, and again in medical industries it is used in prosthesis, etc., which means that the artificial body parts which are being implanted into human body, and this is really used from the ion implantation process, and in luxury products, which is watch component treatments, etc. So this is about the ion implantation process, and now I have a small video to show the ion implantation process.
Alright, we're here at the EB test stand in the Accelerator and Fusion Research Division at Berkeley Labs in the Ion Beam Technology program. And the purpose of this setup here is to implant in the limit single ions into silicon transistors and integrated structures in diamond for exploration of quantum information processing architectures using single spins.
So this is the main feature of our implantation setup. It's an AFM with an integrated ion beam, and here you can see a schematic of our setup. We have an AFM tip and 3 collimators that are both pierced, so we can collimate our ion beam down to a very small spot size. And with the AFM we can scan our area of interest first, can move the tip to like a specific location, and then we can implant the ions where we want them to. And here you can see how our ion setup looks like.
Over here you see a close-up of the chamber you just saw. You see our FM tip and the silicon transistor in which we're going to implant single ions. And with this control here we can position our transistor right underneath the tip, and then by doing a scan of the transistor we can get a close-up and position our tip with nanometer position right where we want it. And with that we can do any kind of patterns we want. Over here you see a pattern of the LBN logo and the logo of our collaborators at UC Santa Barbara. And on the left you see the pattern, how it's going to look later, and this is in a diamond. The spots you see in this picture are about micrometer sized.
Alright, so what we've achieved so far is reliable single line placement into transistors. and we're in the process of establishing a robust single spin readout. We don't have that yet, but it looks pretty good in the scaling, and thanks to our theory collaborators from UC Berkeley, we have a pretty good understanding of what to look for.
So I hope we clearly saw the single ion implantation process on the transistor devices, because as I told earlier, the ion implantation process is used for semiconductor device fabrication, and in that video they used this process to implant single ions on the transistor devices. So thus we have finally reached the end of this first half of the presentation, which is the ion implantation. So next let's see about diffusion coating process. A diffusion coating process is a process in which metal components that will be subjected to high temperature conditions and highly corrosive environments which are coated with a non-corrosive material. The process is normally done in elevated temperature in a controlled chamber. In this process, the alloying elements is diffused into the surface of the substrate, which is usually steel, altering its surface properties. The most widely used coatings are chromium, aluminum or silicon material. In general, this is the process in which the metal is coated with another metal in the process of diffusion coating in order to improve its properties, as well as to make the material a non-corrosive material. The diffusion saturation is possible from various phases, that is from solid, from gaseous or from the liquid state. The saturation from the solid phase is used with iron, nickel, cobalt and titanium, and the saturation from the gaseous phase is used during the coating of aluminum, chromium, manganese, molybdenum and tungsten, and the saturation from the liquid phase is used in the coating of zinc and copper plating. A diffusion layer of usually 10 micron to 3 micron thick may be produced using the diffusion coating. The diffusion coating process increases the resistance of alloy to oxidation, abrasion, heat shock, rapid temperature changes, corrosion, acid, and to improve the other properties of the metals and alloys. Working principle. In chemical gas diffusion or out of contact phase diffusion, the coating material is heated into gaseous form at the distance from the surface being saturated. The gaseous chemical compounds of the coating element react with the base metal, resulting in the diffusion of the metal. This gaseous phase consists of halides to ensure sublimation of the diffusing metal on the base metal surface. This process is usually performed in a very specially designed furnace at the temperature of 700 degrees Celsius to 1000 degrees Celsius, because this process involves high heat, and this cannot be done on an exterior part, because as I told, it involves the very high temperature, so it can only be done on a proper furnace, because the temperature we are dealing with here is typically from 700 degrees Celsius to 1000 degrees Celsius. This is the typical diffusion coating system. It consists of a coating source, power and control system, a vacuum chamber, diffusion pump, a mechanical pump and a Roots pump. This is the real life diffusion coating furnace, and this is how it looks like. This is where the diffusion coating process takes place. The advantages of the diffusion coating process. The advantages of the diffusion coating process is that it has a high adhesion strength between the coating and the substrate, because it has a strong metallurgical bond. The adhesion strength refers to the interrelated strength between the coating and the substrate, which results in the strong force of attraction between them. In addition, the alloyed layer comprises of intermetallic compounds, which can be improved by both the corrosion resistance and mechanical properties. This process can also be used to improve the mechanical properties such as the corrosion resistance and the heat resistance, etc. And the diffusion process makes it possible to increase the resistance of alloys to oxidation, abrasion, heat shock, rapid temperature changes, corrosion, etc., and to improve the other properties of metals and alloys. The disadvantages of the process is that similar to the ion implantation process, the setup for this process is also high, because even this process involves a high furnace and secure place, and partial decarburization of the steel beneath the surface of the carbide layer reduces the hardness and loading capacity of the surface, which is a huge disadvantage of this process. Applications. The diffusion coating process is widely applied to protect high temperature parts from corrosion and oxidation. So we produce a protective barrier by diffusing a metal such as aluminum or chromium into the base metal, which forms a new alloy surface. So by using this process, we just coat the metal and make it resistant to heat, corrosion, abrasion, etc. And the typical application include low and high pressure turbine foils and marine and industrial gas turbines. So these are the applications of the diffusion coating process. So now let's see a video related to this process.
Okay, what we got here is untreated light gauge metal. I'm going to turn on a 3500 degree Fahrenheit torch. OL stands for off the scale. It goes to 2000 degrees. So on the back side, it's off the scale immediately, red hot, and lots of deformation, buckling, cracking. See the cracking here. So next we will remove that. We'll put the same light gauge stud with fireproofing treatment on it. And it's also, as you can see, off the scale. Back side is over 2000 degrees cooler, and no deformation. The metal is not stressing and buckling and so on. So no damage to the structure. Actually, I can probably touch. Yep, see? Not even transferring the heat. So now it's off the scale on this side finally, but still, it's probably 100 degrees or so. Not too bad. Just heat that's coming around the side probably.
So in that video we clearly saw that in the first half of the video there was the uncoated or untreated metal, and it was subjected to heating, and the metal was subjected to deformation and cracking, and the heat was transferring throughout the metal. And as soon as this process was done, and as soon as it was coated using the process of diffusion coating, it was again taken and heated, but on this time the metal was not subjected to heating or cracking, because it was coated, and its purpose was to increase the thermal resistivity of the material, and it was completely resistant because we clearly saw that the person was touching the plate with his hand and nothing happened. So this is the main purpose of this process, to coat the material and increase its properties such as thermal resistance to abrasion, corrosion, etc. So that's it about the video. So finally we come to an end of this presentation, and I hope that you clearly understood about ion implantation and diffusion coating process. Thank you.